Okay, hello. Let's check the sound in the Zoom. Do you hear me? Hello.
Yeah.
Yeah. Okay. Great. Good. Then I guess we can start the presentation. So my name is Mark, and today I will discuss multi-step learning and value-based approximation methods. So let me remind you what Professor Dai presented last time. So basically, we consider Markov decision process with the database. So state position next our state and similar is where so the basic I think that means uh, 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 for so the two for in the function okay the the uh, then uh, have well, uh, the you well uh, uh, is has to uh, as our is even faster cost function is given. In this case, if we know our model, and please come in, yeah. If we know our model, it's easy to find a fixed point of the Bellman equation. So basically, we just need to find a solution of the linear system of equations, the following one. Well, of course, a small problem can occur when the state space is very large. When I say like the state space is very large, I'm talking about like billion or million of states, or maybe infinite number of states. In this case, it's not quite obvious how we can solve like a linear system of equations with like infinite number of equations, or how we can even like multiply pi times g, something like that. So this is like how to solve this kind of problem will be a second part of my, but I wanted to highlight it here. So of course, reinforcement learning considers the problem when p mu and g mu are unknown. In this case, a natural thing to do is, okay, let's say we can basically simulate our value function. So let's take some trajectory starting from x0 and just run our simulator until the end, or until the terminal state, or until that the rest of the trajectory will be negligible. So basically, since we assumed a finite state space, our one-step cost function is bounded, and since beta is less than 1, there will be such n where this term is around 0. So this term is the upper bound for the rest of the trajectory. In this case, expectation of this episode or of this trajectory has to be equal to basically to the value of function. Of course, like one trajectory or one episode is not enough, so we can run multiple episodes and consider and estimate our value function starting from point x as a sample mean. So basically, take like k episodes and estimate g mu x as a sample mean. There are several problems with this approach. First of all, we need to take very long. Usually, we need to take very long trajectory. This implies that the variance of this estimate, even with k, even if we take like k episodes, is very large. Another drawback is we need to estimate value function for each initial x. So basically, for each possible initial for each state from our state space, we need to run multiple episodes. And even in this case, our estimation of the value function will be very noisy. Of course, one can think that another drawback is that we need to store in the memory like each episode, and then only after that we sum them up. But there is a good formula to calculate some sample mean or just means. We can iteratively calculate our estimate as soon as a new estimation of mth episode occurs, we can update our estimation of the value function step x. So formula 1 is basically can iteratively be found from the last slide, from the last iterative equation. Any questions so far? Yes. Okay. So as I said, this approach is possible, but not very convenient and not very. So there are better ways how to do it. One way is the presented yesterday TD0 learning. The main idea of TD0 is based on the Bellman equation. So the Bellman equation that I mentioned before, one Bellman. So basically, we also have expectation in this equation. Then we can assume that in our episode state X, this is the initial state for our system, is visited multiple times. So is visited at time km. So in this case, we can also estimate our value function as a sample mean, theta. In this case, we will also need an estimation of the g mu xkm plus 1. So summation of the value function of the next step. So basically, for each state from our state space, we basically can use this sample, like iterative updates for this sample mean. And in this, as a result, we can get a TD0 learning. So this is intuitive explanation of TD0. So last time it was more rigorously explained how we can get TD0 learning. So basically, in this case, we update value function or estimation of the value function, not only for one initial state, but for each state. So in this case, the variance will be less because basically we estimate GKX only based on the one step plus estimation of the value function. So convergence of TD0 learning is much better than just Monte Carlo approach. However, there is a drawback. If the initial estimation of the value function or initial guess of the value function, so G0 is bad, so it's far from the true G mu function, then it can take a lot of efforts to reach to get a good estimation, because as you can see, like the previous estimation of the value function makes a lot, like we have a lot, we can see the previous estimation like in 2 terms. So it's very important to have a good previous estimation of the, like a good estimation of the G function in the previous step. So there are two good, so there are 2 algorithms that we have considered so far. One is Monte Carlo approach, another is TD0 approach. So basically, in Monte Carlo approach, we run the trajectory until the end. In TD0, we basically need to make only one transition and then update our value function. In Monte Carlo approach, we need to run until the end and then we update our value function. So we basically want something in between. So something in between is n-step TD learning. So the idea of n-step TD learning is based on so first of all, we define n-step Bellman operator. So it's it's the following one. And then we get from n-step Bellman operator, we can define Bellman equation. So as you can see, n-step Bellman equation should have the same fixed point, so should have the same solution. G mu as a classic Bellman operator. Because basically, if we come back to the Bellman operator, so basically in n-step Bellman operator, we take like t mu, operator t mu from both sides, and like do it multiple times, like n-1 time. and we get like n-step Bellman operator. So solution of this n-step Bellman operator equation has to be the same as just zero-step Bellman equation. Yes.
The right-hand side repeat the mu.
Here, I mean, here I'm just writing down a Bellman equation, so I don't want to write. Of course, the solution of this Bellman equation or of this fixed point problem will be G mu, but equation is the following one with respect to G, and so the correct solution of this equation is G mu. Yeah. So in this regard, you are right. So what is the n-step TD learning? Basically, at step xk, we wait n times. So basically, then we after step xk, we make like n times step and estimate. And while we make this transitions, we accumulate the following cost. So in red, so after n iteration. Plus, we can estimate the rest of the trajectory based on our current estimation of the value function in the state xk plus n plus 1. So this one, so this estimation is something in between TD0 and Monte Carlo approach. So in TD0 or like zero-step TD learning, we basically take n is equal to 0, and we only have like one term in this like red summation. In the Monte Carlo approach, like we run our episode until the terminal time or until so based on this idea, we can get update state for n-step TD learning. So it's it's very similar to TD0 learning, but to update estimation of the xk, we need to wait n time step after we have visited xk. So this is a sort of drawback of this algorithm, because in TD0 we update like after one step we update estimation of state of value function of step xk immediately. If we go back, so basically we make one iteration from xk to xk plus 1 and update our estimation. In the n-step TD learning, we need to wait n steps. I mean, so this is a drawback because one can say that estimate. So since our learning is slow in this regard, so this n-step algorithm is worse than TD0. On the other hand, we can see that when we update xk, so the value function at xk, our estimation is better, because to update the value function in xk, we use n time steps, information from n time steps. And in this regard, our update, we hope that our update is better.
Hi, Mark.
Yes.
Can you hear me? Okay. So can I change n from iteration to iteration? Capital N.
Basically, you can. There's
Yes,
no.
I can, right?
Yeah.
So then I would instead of wait for to update a particular x, I would just run my Monte Carlo. Whenever I see a state has been repeated, then I just go ahead and update that particular thing right away. When I see something else being a state repeated, and then the update the next one. Can I do that?
Basically, you do a Monte Carlo approach.
It's not Monte Carlo, but I update the value function for a particular state whenever that state is repeated. You see what I mean?
So basically,
I don't look.
yeah.
I don't fix this X. I don't say, hey, this is the X state. I want to update this guy. I just run my Monte Carlo. Okay, keep running it. Whenever I see a state has been repeated, I go ahead and update that for that particular n. How many times that has repeated?
Yeah, of course, but,
and then if something else in the meantime repeated again, I go back to the history. Oh, this has started from that particular value. I update about that particular J value for a different n for that particular state. Is this approach? I mean,
what if you do not do not come back to to some state? So you need to run it until then, basically.
Well, but this if that will have the same problem here. If it's n step, if nothing is repeated here, you don't update anything here, right?
No, there is
the n step thing. You also keep running it until don't you count the number of times it gets repeated? It's repeated. Then you update, right?
No, there's no assumption that any state will be repeated. So basically, we run n time step, like fixed number of steps, and then update.
Then I got. So I see. So, but this T0, it's repeated. You have to only at TD0. You wait for the state to be repeated. You mean?
I mean, no. I mean. So you mean like the second item? The second item is not quite a good way to think about it, because this is like intuitive way how one can think about TD0 learning. But basically, we don't wait until one of the states.
Oh, you don't wait anyways. You keep updating it. I see.
Yeah,
okay.
We can update like. So you can see the right.
So I was misled by this book.
Yeah, I mean, this is maybe, yeah. I mean,
but like, you can do variable. This n can vary from state to state and from iteration to iteration. You can do TD0 and then do TD1, TDK, TD5. I mean, coming back and forth, right? Well, this will all work, right?
Yes.
Okay.
And like, okay, let me go further, and there will be a similar argument that we are discussing. So basically, so there is a problem how to choose n, basically, because in this n-step TD learning, we have a fixed n, and it's not obvious how to choose it.
Yeah. So in practice, how do you choose this n?
In practice, usually people choose something in between. So the best results is if you have, I don't know, something like people try many, like 10, 9. I mean, it depends on the problem. So, but the algorithm that is more popular than n-step TD learning is TD lambda. So the idea of TD lambda is basically that we assume that our n is geometrically has a geometric distribution with mean lambda. In this case, we can define a lambda-weighted multi-step Bellman equation. So the following one. And in this case, lambda-weighted multi-step Bellman equation will be equal to the last one. So why we consider the following lambda-weighted multi-step Bellman equation? In this case, instead of choosing some specific n, we basically can vary lambda, so from 0 to 1. Also, we there is a better better variance. The variance will be less for this Bellman equation in theory. So basically, if instead of choosing like some fixed n, we assume that n is following some geometric geometric distribution, we can get a lambda-weighted multi-step Bellman equation. So this is a Bellman operator for T mu lambda, and if we apply this T mu lambda operator to
Mark.
Yes.
So how do you choose this lambda in practice?
In practice, you try like you try many options of that. Usually in
values,
practice,
okay.
so there is usually like in practice something like lambda close to 0.5, 0.6 works the best. But it depends on the problem, and usually if you have lambda close to 0, that means that so lambda is equal to 0 is basically TD0. For TD0, agreeing the variance is very low. On the other hand, can be biased. So if lambda is close to 1, is basically Monte Carlo, or if when lambda is equal to 1, is basically a Monte Carlo algorithm. So usually people like choose something in between, so something 0.5, 0.6, 0.7 work the best.
Okay, so
there is no
why
like,
geometric distribution? You could choose other distribution in theory, right?
In theory, yes. But the thing is that if we choose like this distribution, then like sums in the last line are finite. So it's so in theory, of course, you can choose any distribution such that like sum like sum of your like operators.
There's a weighted average of these finite.
Yeah. So if we can consider like I don't know, nu is some uniform has a uniform distribution, then there is no guarantee that like sum is convergent or something like that.
The uniform O infinity. I mean, this is not working.
This is something strange. So.
But any probability distribution between 0 and infinity over integers, I think, should work, right?
Yes. Yes.
Okay.
So let's so we consider the lambda-weighted multi-step Bellman equation, and after like several steps, like very technical steps, like changing the sums and so on, we can write our Bellman equation as g mu x k is equal to like expectation of some sum plus g mu x k. I should note that this DMK in the last line is called a temporal difference. So basically, so our Bellman operator can be written in the following way, where D is a temporal difference that is defined in the last line. So then we lambda-weighted Bellman equation is the following one, and we can do online iterations of this algorithm. Of course, online iteration, so we can see that there is an infinite, so sum up to the infinite. And of course, we cannot afford to run like to run infinitely long trajectory, although we assume that we have such infinitely long trajectory, but we want to update our estimation of the value function online. So as soon as we do a step, we want to get a new estimation of the value function. So the goal is, so based on this lambda weighted Bellman equation, we want to create some online version of this algorithm. So basically, instead of summing up until the infinity, we want to sum until so as many temporal differences. So temporal differences depend on iterations. So basically, okay. So if we want to calculate g mu plus k, so when m is close to infinity, we need to we need to have a trajectory until m. So until state x m k plus 1. Or basically, we need to make like m plus k plus 1 times time steps. So of course, it's very long to wait until infinity. So how can we calculate this sum iteratively? So basically, let's assume let's do it step by step. So let's consider the first iteration. The first iteration, we basically move from x0 to x1. So if we go back to Bellman equation, so basically we have that k is equal to 0 and m is equal to 0. In this case, we basically calculate gxk 0 plus gamma d0. So basically, we want to calculate this infinite sum like iteratively. In the second time steps, like after the second time step, when we have moved from x1 to x0, from x1 to x2, we want to update already to estimation of the value function in two states. First, we want to update value function estimation at x0. So one more time, so our estimation from x0 is g mu. So g mu plus. So in this case, k is equal to 1, m is equal to 0. So one more time, g mu x1, we get x0. So because we updated at x0 plus, we calculate. So we have this sum. We already done like 2 time steps. So m is equal to 1, and we update. So k is equal to 0, m is equal to 1, and we update to sum like lambda b d1. So this is what we get here. So here we already used an estimation from the first iteration. So if we substitute a transition from x0, so estimation after the first step, we get the following estimation at x0. So for the state x1, we made only one iteration from x1. So m is equal to 0 in our sum. M is equal to 0, and basically we get the following current estimation of this sum. And we can continue in the estimate the infinite sum in the following regard, but there is a problem. There is a problem. What if, for instance, in the second iteration, x0 is equal to x1? So there are two equations. Basically, we have two equations. How we can update estimation of the value function in x0 or when x0 is equal to x1. So basically, we can update estimation of value function according to the first one, according to the second equation, or some combination. So it's unclear what G2 at x0 should be. Should be like this one, like the first line, or the second line. There are multiple ways how to consider or how to solve this problem. Basically, there are people usually use three variants of TD lambda algorithm. One is restart variant. So basically, we basically substitute. So basically, we substitute estimation from the first time step. So G1x0 is equal to G mu x0 plus gamma d0. We substitute this estimation in the second equation and get the restart formula or the restart variant of TD lambda algorithm. So this is one way how we can calculate G2 x0 when x0 is repeated. Another variant is first visit variant. So first visit variant, we basically ignore that our state has been revisited, and basically we ignore the second equation, and our update follows the first one. And another variant is the every visit variant. So basically, we combine two equations. And our update is our update of the value function is and at state x0 is the sum of update from equation 1 and from equation 2. Any questions? So d0. So let's d0 is temporal temporal difference. Yes, this is the last one. So basically, we wrote our Bellman equation such that it depends on these temporal differences, and it's easy to consider or to understand TD lambda algorithm based on temporal differences rather than so we can just substitute G plus beta lambda estimation of value functions in our updates, but it's easier to think about TD lambda based on this problem. Any other questions?
Can you go back to the previous earlier page?
Yes.
Another one.
This one?
No. Yeah, this one. This one. Yes. No.
This?
The previous one.
11.
But, yeah.
Okay.
No. There's a delay before.
So 9. This one.
This one. Yes. No.
Okay. No. So let's start. So this one.
N step PT.
This one.
No. This yes.
One? This one. Previous. This one.
Yeah. TD learning. Yeah. This one.
Okay.
So, is there something wrong here? So, if you look at this equation, you have J mu xk on both sides of the equation in the start and the beginning, and then you have something.
So you mean that we have G mu xk here, like on the left side, and G mu xk on the right side?
Right. Is there a weighting factor somewhere?
No, I mean there was no G mu xk on the right side. So basically, just technically, we wrote technically we wrote equations on the right side and get G mu xk. We added and we made plus minus G mu xk. So it's the formula is correct.
That means the expectation turns 0.
Yeah, when we go when we sum until the infinity, the expectation of this should be of this term should be 0. That's true.
Okay, so I see. This is a difference. Now, how is this used? Okay, I missed. I was away for a few minutes.
Yeah, so we have lambda weighted Bellman equation. So you have G mu on the left side and G mu on the right side. So I just wrote what was on the previous slide.
Now, how do you get this top equation from the previous page?
On the previous page, so okay, let's go maybe from this step. So basically, this is the first one is just a definition of lambda weighted Bellman equation. Then I exchange like the sums, like this infinite sum with this finite sum. Then on the left term, I need to add and like to make plus and minus g mu xk to get like these temporal differences. So because as you can see, this sum, like the sum in the third line. In the third line, you have like the sum from n is equal to 0 to infinity. And if m is equal to 0, there is a term g mu xk plus m. So basically, we have minus g mu xk term. So we like minus g mu xk plus, and we need to add this g mu xk term.
Mm-hmm. Okay.
So this is, yeah. So then we like basically wrote our Bellman equation the following way. Then when we have expectation, basically we can and we have estimation of the term inside. We basically can update our estimation like in online fashion. So like a new estimation of in the state gk is equal to gk plus. So basically, then in the brackets, in the square brackets, we have like this expectation term minus gk x. So basically, we do like online. We update our estimation in online fashion. So basically, then like gxk and like we have g plus gxk minus gxk. So this will cancel out, and we'll get like that an update formula for for the estimation of gxk in the second equation.
Yeah, but this is not really online because you have summation to infinity of this d bit.
Yes. So then basically our goal is to estimate this summation like until the time that is possible. So if we, for instance, we made only like x, so we have done like n time steps or like n iterations. So basically, we can estimate this sum until n. So we want to create an algorithm that like calculate this infinite sum iteratively. So, and if we assume that we have a single infinitely long trajectory and we run our algorithm infinitely long, then asymptotically it will converge to the right answer.
Okay.
Okay, so so our goal is basically to estimate or to calculate this sum iteratively. So for instance, if we have made only one transition from x0 to x1, we can in our formula k is equal to 0 and m is equal to 0, and we update our estimation already. We were like only after one iteration. So when m is equal to 0, so basically this is gx 0 plus gamma m is equal to 0, so it just d0. You get only d0. So basically the goal is to, as soon as we have made a time step, we want to get a better estimation of the value function. And we estimate like this infinite sum as good as we can, on the information that we are that is available for us until like some until the current time step. So let me repeat. So in the second iteration, second time step, we can update. So if we have started from x0, so from x0 we have made like 2 time steps. We have two iterations. So we can now estimate or calculate our infinite sum from m is equal to 0 to m is equal to 1. So we have like two terms here. So one term is g0 basic gx0 like in the second equation, the first term, and then like we have made like 2 iterations. So m is equal to 0. So m is equal to 0 and m is equal to 1. So we get like two terms for to estimate a gx0 after the second iteration. On that, but for x1, from x1 we have made only like 1 iteration. So we have information only from 1 iteration to update g2x1, and there is only one term. Of course, there is a problem that when x0 is equal to x1, and then there are, and because it's not obvious how we need to update what is g2x0, because we have like 2 equations now to update. So basically, we have 3 variants how to combine these like two updates for g2x0. So basically, based on these like 3 variants, we can write our sorry, the update equation for TD lambda. So I'm skipping the some explanation why we can write like our algorithm or our iterative estimation of this infinite sum in this equation in first equation. But basically we can estimate so after we make 1 time step, we update each estimation of the value function for each x in our state space. And in the previous slide there were like 3 variants how we can update it, and this is like 3 variants how we can calculate this term zkx. So this is once again I'm skipping explanation why it's just the final equation for TD lambda updates. I mean, we assume that we can sample according following mu poles. So all our trajectory. So to make to choose actions, we choose actions according to mu poles. Yeah, I believe there is off policy TD lambda. There is such algorithm, but I don't don't want to consider it here because like I see that even like explaining idea of TD lambda is quite tricky. So this was the first part of my talk where we considered multi-step learning. The second one, in the second part, I want to move to approximate dynamic programming. So as I mentioned before, there is a problem when the state space is very large. First of all, if number of steps in our state space is like billion or million states, then like even like calculating like in a product is time consuming. Moreover, there is a possibility that even like storing a vector, so a value function for each state is impossible. So for instance, if our number of like our state space has infinite states, then of course it's impossible to store like a value function for each state in a computer memory. So in this, to overcome this problem, we can approximate our value function. So let's assume that tilde g is a function that we will use as an approximation of a true g mu function. We assume that this tilde g function depends on the parameters r, where I is from where vector r has dimension s that is much smaller or very small compared to a number of states in our problem. So for example, we can assume that our estimation of the of the value function is equal to, it has some linear form. So it's just a combination of some, or a linear combination of the feature functions. So basically we choose some finite, very small set of functions like phi1, phi2 up to phs, such that we can easily calculate like phi k of x. And we consider like a linear combination of these feature functions. Another possibility is, of course, assume that our value function, we can approximate our value function as a feed-forward neural network. For instance, here I just I gave an example of feed-forward network with like one layer. So in this case, we have like parameters r that depends on k, whereas k is number of neurons in this single hidden layer, or like and r k l, whereas l is dimensionality of the vector. So x is encoded as an l-dimensional vector v x. So basically, we also, if we consider neural network as an approximation for the value function, we also can think about this estimation as something that depends on the current, on the state, and on parameters r. Questions? No? Okay. So of course, the easiest and like the basic form for value estimation, for value approximation is a linear form. And most theoretic results are given for this kind of form. So we want to estimate the station value function for the stationary policy. I mean, this is just a definition of the value function. So we assume that our approximation for this g mu x is equal to some linear function. So it has a linear form. I also wrote like this sum as an inner product where phi x is S-dimensional feature vector. So phi x is basically is a vector that is equal to phi1x, phi2x, and so on. Also, to make it even more complex, I can write estimation of the value function as a matrix phi that has feature vectors phi x as rows multiplied by our parameter vector r. So in this case, so this estimation of the value function tilde g will be, so this is tilde gr is a vector, whereas each entrance of this vector is an estimation of the value function for some specific initial state. So basically, if we wrote, so as we wrote our estimation, we want to approximate our value function within space S that is equal to phi r, whereas r has a dimensionality S. So this is just a subspace of our. So S is can be considered as a subspace of the space of the state space, the space X. So our goal is basically to find the best approximation tilde G star with respect to some weighted norm. So basically, we want to minimize the following norm, so that the difference between G mu and tilde GR is less as possible, according to some C weighted norm. That I will tell what is C weight. So this problem is equivalent to finding the best parameters such that so we can write equation optimization problem of finding tilde G star is an optimization problem of finding best parameter R star. So in the second equation of this slide. So basically, we are trying to solve. We are trying to find projection of vector G mu that is in the. So this G mu can be considered as a vector in the state space. So that has a huge dimensionality. On the other hand, we have space S or S that has a lower dimensionality on the S. So our approximation, best approximation, phi r star or tilde G star is a projection of G mu onto S with respect to C weighted norm. Any questions based on this slide? So basically, we have a vector in very large space. We have chosen a smaller subspace, and the goal is to find a projection from this of this vector G mu on the small subspace. So then, like this, the best parameters G star will be equal to this projection, to phi r star. So phi r star is our best projection in the equation. So to move to move further, we need to assume that if we apply a Bellman operator to the best estimation or to the best estimation of the value function, it has to be equal to G mu. So one can think about it as, let's assume that our approximation is exact, so that P R star is equal to G mu. In this case, we just get the Bellman equation. However, it's not usually possible that our linear form or linear architecture recovers the correct or the exact G mu. So we need to make an assumption as in equation 3. Then combine 3 and 2. So 2 is that equation 2 just says that our best approximation is just a projection, and with our assumption in equation 3 we basically get the following estimation, the following projected Bellman equation. So we want to solve a projected Bellman equation, equation number 4. This is that we get combined 3 and 2. Yeah, but sort of. Yeah, because here it will be exactly like Bellman equation if like our approximation P R star is exact. So basically, if instead of P R star we'll substitute G mu, then of course we get like equality, and this is Bellman equation. So of course, if our estimation is not exact, then it's approximate. We only can assume that it's approximate. So now our goal is to solve the projected Bellman equation. One can show that combination of projection and Bellman operator T mu is a contraction operator with respect to the C-weighted norm that we have considered earlier. But this C, like this weights, has to be equal to a station distribution of the Markov chain associated with the policy mu. So we can choose like this weights as a stationary distribution of the Markov chain. Then pi T mu is a contraction mapping. So since this is a contraction mapping, we can hope that as a result, our equation 4 is basically a fixed point problem with a unique solution. So we can write equation 4 based on the definition of the projection in the following way. So basically, the first equation says that if we project like our T mu phi r, that is minus G mu plus beta T mu fr star. Then R star is the best, so our projection PR star is the best. So this is just a definition, like first equation is just definition of the projection. So we get this optimization problem, and we take a gradient of this optimization problem with this, and set it to 0. So we get a new linear set of linear equations. However, the problem is that we don't know D, that is equal to D is a diagonal matrix with our stationary distribution on the diagonal. So we don't know this D. Also, we don't know G mu, P mu, and phi. Phi is also a high-dimensional matrix. So how can we find a R star that is a solution of equation 5? So equation 5 can be compactly written as C R star is equal to D. So basically, we just write equation 5 in the as a system of linear equations. C R star is equal to D. Whereas there is a description of what is C and what is D. So based on equation 5. Any questions? Yeah. No, I mean, we get this equation as a projected Bellman equation. So let's say you have team U phi R star right here, right? So this is maybe I should, yeah. Then you take so this is some vector in your like big state space. Then you project this this team UFR. Yeah, that is like then you project it. As a result of this projection, you have to get phi R star. Yeah, like here. So that's why we have R star like inside the node. So definition of the projection. The projection is the so a vector. So projection is the closest point in the subspace to the original vector, right? So the closest point to p mu phi r star has to be equal to phi r star. So that's basically what the first equation says. Okay, good. What time is it? Okay, then I will I'll try my best to finish. So that's okay. So basically, then we want to solve this compact set of linear equations. So we just write C mu CR minus D, and we get, like, if we substitute the definition of C and D, we get the second term. And the second term, we can see that the second term is basically expectation, because expectation with respect to balancing mu of the following term, the last term. So basically here we have vector, right? So so D is a metric, a diagonal matrix with a station distribution diagonal. So here, so this is expectation with respect to this station distribution. So so an equation CR minus D is equal to 0 is equivalent to solving R is equal to R minus gamma CR minus D. So if CR minus D is equal to 0, so basically we get R is equal to R. Then we substitute CR minus D, and basically given episode, we can get TD0 algorithm with linear approximation. So this expectation can be considered as So each time we can estimate this expectation based on one condition. So we substitute xk instead of x, xk plus 1 instead of y, and we get an update formula for our parameters r. So this is TD0 algorithm with linear approximation. Then there is a convergence proof that was given like almost 1 year ago, that if the Markov chain associated with policy mu is reduced to an aperiodic, if we choose a learning rate accordingly, that then TD0 converges to R star, that is a solution of projected Bellman equation. And that is the most important, I guess, that R star satisfies the following error bound in the bottom of the slide. So you can see that at the end, our estimation, the best estimation, phi R star, depends on basically on our choice of the subspace, of the difference between projection of the G mu minus G mu, and it also depends on the discount factor. So you can see if discount factor is very large, for instance 0.99, that usually is used in the many problems, then this estimation of this TD0 algorithm is even if it has converged, the estimation can be very bad. Okay. I guess this will be my last slide. So, of course, the convergence proof of this TD0 algorithm with linear approximation was given 20 years ago. But for example, a final sample analysis for this algorithm is basically ongoing research. So what I mean by final sample analysis is basically how many time steps, like how many final time steps you need to do to get to like some error. So basically, so the error between, so you have after like n time steps, you get some estimation of your value function of the parameters r, right? Then the difference, let's say you want to have the difference between phi r star and your current estimation less than epsilon. So the question is how many steps, like final steps, you need to make to get to this error. Not clear? So one more time. So the algorithm is converging to phi r star. But after like some finite number of steps, let's say n steps, you have estimation of r like rn. And your estimation of the value function is phi rn. So the question is, what is the error between phi r star and phi rn? So let's assume you want this error be less than epsilon, according to like some norm. I don't want, like, maybe like this norm. So the question is how many steps you need to make, like how many iterations of TD0 algorithm you need to make to get to this error. So this is like there is a finite number of steps that you need to do to reach some like epsilon error of your estimation. Iteration of the TD0.
Yes, but
or number of updates of R parameters R. So our trajectory always follows mu poles.
yes, yes.
No, here we assume that like our actions are following like our new poles. However, for instance, 1 year or like 2 years ago already. So people have proved some of this convergence rate of finite sample analysis on the assumption that we can sample, like your question, RD samples from a steady state distribution. So basically, TD0 algorithm is based on that we start from some state and then we follow new poles. But there is no assumption that our initial state is a steady state distribution, because we basically start from some like determined initial state. So if our Markov chain is ergodic, it can take some time to reach like steady state distribution. However, this 2 years ago, people had to assume that they can generate ID sample from the steady state distribution of the Markov chain associated with mu poles. 1 year ago, people were able to derive a convergence rate for projected TD0. By projected, I mean that they pre-assumed that RK is bounded by some number. So, and if the TD0 algorithm at some point of the algorithm GR is greater than R, they just projected. So they use information theoretically to get this bound. And quite recently, we found a convergence rate for the original TD0 algorithm. So basically, this result was presented like here in MIS workshop in December. So maybe some of you have visited this presentation. Yeah. So convergence was. I mean, he hasn't Lean hasn't published this paper yet. So he just presented on the conference one month ago, basically this result. But the point is that even for this simple algorithm, TD0 with linear approximation, still there is ongoing research for some basic, even for the basic equations like convergence rate of this algorithm. It's still was open until a month ago. Okay, I guess I will skip the TD0 and LSTD0. Of course, there is limitations of TD. So we just consider a policy evaluation. So given policy mu, we have found a value function. However, we haven't considered policy improvement, how to improve policy. And there are limitations with this approach, because if we will use estimation of G mu policy, there is no guarantee that still the G mu greedy policy is better than mu policy. And there is policy oscillation and chattering often occur. Okay, there are references to the papers that I used in my presentation. And I guess that's all. Thank you for being here. Any questions? Yeah, I guess so. Okay, thank you. It's you mean the result? The results. I guess Lean presented that it should be linear, sort of. I mean, I don't remember his result exactly, but I mean, yeah, it's converging, but the problem is how many steps you need to make to reach some guaranteed error. Because I mean, you cannot like do a infinite trajectory. You like in practice you like do some finite number of iterations of steps, and people usually want to have some guarantees that okay, if we make like n transitions and like iterations of the algorithm, you'll get like this error. Basically.
Like, or
Yeah, so basically the curious fact is that so I mentioned 3 papers, like 2 years ago, 1 year ago, and like current research. Like 2 years ago, they used like very like recently developed stochastic approximation techniques. 1 year ago, they used like information theoretic techniques, and the last like Lean used like Stein's method. So for the same problem, people use like different approaches. And it's like quite interesting. So I mentioned all these like 3 papers. Yeah. No, that ID samples from the station distribution was assumed only for the first paper. For the second paper, they didn't assume that. So they assumed they like followed the classic TD0 algorithm. So based like starting from any state, we will run our algorithm. On the other, but the point is that they still had to assume that like that they can use like projection that is not used in the original TD0 algorithm. So it wasn't like, and they couldn't like get rid of this like technical assumption that they will like project like parameters RK if they very large. So to get some estimations of the convergence, and like the final paper, like the final result was like original TD0 algorithm. So without any assumptions in the projection and without assumption that we can sample from steady state distribution.